Well, good afternoon, everyone. My name is Angel Sharon Sadavan Babu. I'm from the United States, just outside Washington, D.C., our nation's capital. And I'm super excited to talk to you guys today about my research project, EEG signal analysis for early detection of REM sleep behavior disorder as a prodromal or early marker of neurodegenerative disease. So without further ado, let's begin. So, picture this. It's the middle of the night and you hear something in your parent, sibling, friend's room, and of course you're concerned, so you go in to check on them. What you see leaves you shocked. They're kicking, punching in the air, screaming vulgarities. In fact, they're moving so much they fall off the bed, injuring themselves. Now you might be thinking, wow, that's just a really bad nightmare that they're having. However, it could be something way more than that. You could have just witnessed an episode of rapid eye movement sleep behavior disorder, or RBD for short. So what exactly is RBD? The formal definition is a sleep behavior disorder characterized by abnormal behaviors and loss of muscle atonia, or muscle paralysis, during REM sleep. And it's most notably seen through dream enactments. In the general population, RBD affects about 0.5 to 2% of the population. But in older adults, that number increases to about 5 to 13%. And while it occurs equally in men and women, men over 50 show it more likely because women exhibit less violent symptoms, so it's underdiagnosed for them. So what exactly happens in the brain during an RBD episode? Normally, during REM sleep stage, when we dream most vividly, our bodies are paralyzed to keep us from acting out our dreams, otherwise known as muscle atonia. But people with RBD lose this muscle atonia. In addition, the brainstem regions responsible, including the subcutaneous nucleus and the magnocellular reticular formation, break down. This resulting behavior is violent dream enactments, both verbally and physically. That means they might talk, kick, punch without remembering a thing. And while RBD only affects a small percentage of the population, you might be asking, why should we care about this? Why should we study it? Interestingly enough, however, RBD is often caused by the misfolding of a protein called alpha-synuclein, and it's often the first sign of something deeper, neurodegenerative disease. Next slide. So, there are two types of RDB: idiopathic, meaning it comes without any underlying cause, and symptomatic, which means it results from a brain injury or medication. For the purposes of this presentation, we will be focusing on idiopathic RBD because it's widely attributed as a prodromal marker or warning sign of synaptopathies, very long word, like Parkinson's, dementia with Lewy bodies, and multiple system atrophy. In fact, 80 to 90% of people with RBDs will eventually develop a neurodegenerative disorder. In fact, studies show that RBD can appear years, sometimes decades, before full-blown symptoms of these diseases occur. So this gives us a special opportunity, a small window. If we can detect RBD early, we may be able to intervene before serious neurodegeneration sets in. So, in order to diagnose this, we need to look at current measures that are being used. So the current gold standard for diagnosing RBD is polysomnography, which is a comprehensive sleep study that records brain waves, oxygen levels, and body movements. However, this process is expensive, time-consuming, and not widely accessible. We also have basic questionnaires like the RBD screening questionnaire, but these rely on self-reporting, which isn't always reliable. In addition, differential diagnosis is used, because RBD is often overlapped with other sleep disorders, like sleepwalking or obstructive sleep apnea, which makes it more difficult for it to be diagnosed. So this leads us to the big challenge: how to make early detection affordable, accurate, and scalable. Next slide. So this leads me to my overall research question. Can we detect RBD earlier and more affordably using EEG data? The idea is simple but powerful. Use machine learning algorithms that learn patterns from data to analyze EEG recordings and detect RBD before symptoms escalate. If we can extract meaningful features from these EEG waves, we could revolutionize early diagnosis, not just for RBD, but for these neurodegenerative diseases like Parkinson's that follow it. So for the first part of my research journey, I looked into current literature about this specific subject. Recent studies show that RBD patients have reduced EEG complexity, meaning that their brain activity is less chaotic. Therefore, machine learning models can be trained on REM and slow-wave sleep stages, and these models are already hitting great strides, with having over 90% accuracy in classifying RBD. Deep learning models are also being utilized, such as convolutional neural networks, and have been used to predict whether someone with RBD will later on develop Parkinson's. So the key takeaway is they're reliable EEG biomarkers for RBD, we just need to harness them. So to follow, I followed a very detailed, very structured research pipeline to test this experiment. So I followed 4 steps, the first being signal acquisition, or collecting or acquiring the EEG data, pre-processing, which is cleaning the data and focusing on meaningful frequency bands, feature extraction, which is pulling out different features of the EEG wave that represent the brain's behavior, and finally, the most important part, machine learning, which is feeding these features into machine learning models so that I can learn patterns and then make predictions based off of that. So the first step is the data set. So I used a public data set called the CAP Sleep Database from the Sleep Disorder Centers in Parma, Italy. It has 108 recordings, 16 of which being healthy individuals with normal pathology, and 92 being patients with various sleep abnormalities, RBD of course, think insomnia, narcolepsy, and others. So these recordings, as you can see right here, are not just EEG signals. They include various biomarkers such as EMG, which is muscle activity, EOG, which is eye movements, breathing patterns, and more. These recordings were labeled using the Refscafson-Kale system, a classic method for sleep staging, and also include CAP phase annotations, which track microarousals in sleep. And so for this specific project, I only worked with a small database due to the limited amount of recordings. I used 10 patients with normal pathology and 10 patients with RBD. So the next step is EEG pre-processing. So I took the raw EEG signals that are noisy, and they have a lot of artifacts, so blinking, muscle twitches, and even artifacts from the recording machine itself. So it's important that we clean them up. So therefore, I use fast Fourier transform, or FFT, which converts these signals from time domain to the frequency domain so we can analyze these brainwave power at different frequencies. And I use the bandpass Butterworth filter, which filters out irrelevant noise and keeps the useful frequencies, which is between 0.5 to 50 Hertz, which is the standard range for EEG studies. And so this helps us isolate the patterns that matter most for detecting RBD. And as you can see here, this on the top is the filtered, and on the bottom is the non-filtered. As you can see a little bit more definition with the filtered, so that's exactly what we want. So now we go on to feature extraction. For the purposes of this project, I separated the features into 2 sort of classes, the first one being time domain, and the second one being frequency domain. So first, time domain. I used various features, so the first one being mean, which shows the average signal level, variance, which indicates how much the signal fluctuates, root mean square, which gives us a sense of the power in the signal, and a lot of features regarding the peaks of the wave. So peak to peak amplitude, number of peaks, this gives us a feel for how high the signal is. And these features will tell us the intensity of brain activity and variability, which is useful for detecting signs of neurological instability. So next we have the frequency domain features. I isolated 2 features in this category, one being spectral power and the other one being dominant frequency. Spectral power being how much energy is in each frequency band, and dominant frequency is what frequencies are the strongest in these signals. I focused on standard EEG bands, delta, theta, alpha, and beta. And these detect characteristic disruptions in the spectral balance during REM sleep, and it's especially important because RBD shows increased theta waves and shorter alpha bursts. So it's really important in isolating those features in order to differentiate between healthy patients and patients with RBD. So, with all these features, I compiled a correlation feature matrix, which is basically, as you can see, a big chart of all these extracted values and how they correlate with one another. So, features like RMS, variance, spectral power, and peak-to-peak amplitude are highly correlated, suggesting they capture similar signal magnitude information. In contrast, features like dominant frequency, skewness, and kurtosis are less correlated with each other, indicating they offer unique and complementary insights into the signal's frequency and shape. Therefore, I removed the redundant features in the machine learning step, which I will talk about next. So, now for the big part, machine learning. I wanted a supervised classification system to distinguish between RBD and healthy subjects, since there's two distinct classes. Therefore, I tried 3 supervised learning models, the first one being support vector machines, which are great for finding decision boundaries in complex data, and they work by having a hyperplane that best separates classes in a high-dimensional space. And as you can see on the top, that is a diagram showing the support vector machines. Next, I utilized random forests, which combine multiple decision trees to improve accuracy. And it averages out the predictions of many individual trees and reduces overfit and improves generalization, so making it powerful for classification especially. And the final algorithm I used is XGBoost, which you can see here. It is basically a highly efficient and scalable use of gradient boosting, and similar to the random forest, it uses decision trees sequentially, where each new tree tries to correct the errors of the previous one. So after running through all of these machine learning models, I then used what is called a K-fold cross-validation. In my specific project, I used a 5-fold cross-validation system, meaning I split the data into 5 parts and trained it on 4 and tested on the 5th, and rotating each time. This is especially important because of the small data set I have to prevent overfitting, especially because if you have too little data, the model might just go to all the points without making a clear generalization if you have a bigger data set. So this improves overall accuracy in the long run. So now for the results. So after training and testing all the models, I created confusion matrices for each of them. And basically what these tell you is how many true positives, true negatives, false positives, and false negatives the model went through. And so as you can see, we have our F1 score, which this number means the accuracy, and then this one means the standard deviation, or how spread out the values are. So we have that final F1 score. As you can see in the middle, the random forest classifier performed the best, achieving an accuracy of 80% across cross-validation folds. And you might be wondering, since there are 2 in the true positive, 2 in the true negative, why is it not 100%? Well, like I said before, we use the 5 cross-validation systems, so therefore at each time, it may not have been 100% despite what the confusion matrix is showing us. So therefore, that's why it's 80% and not 100%. This demonstrates that the model's ability to generalize well despite the limited data set. And key features such as spectral power, RMS, and dominant frequency emerged as strong indicators for REM sleep behavior disorder from normal EEG patterns. So overall, like I mentioned earlier, random forest performed the best, while XGBoost and SVM underperformed. However, there's a simple explanation for this. Like I said, despite the 5-fold cross-validation, there could be some risk of overfitting, considering again the small data set we had, with only 4 that were being trained. Despite this, the model's performance indicated a strong signal separability and confirms the feasibility of these automated EEG-based RBD detection. So therefore, with future data and tuning, this approach could contribute meaningfully to early diagnosed pipelines in sleep medicine and neurology. Okay, so where does this leave me? What are the future implications of my research and clinical implications in general? So the future implications could be groundbreaking. These types of machine learning models could enable low-cost EEG-based screening in outpatient and home settings, and it could identify high-risk individuals for early intervention in these neurodegenerative diseases like dementia with Lewy bodies, like Parkinson's disease, which we all know is plaguing the world today. With other comprehensive diagnostic tools like polysomnography, we can create a robust system for diagnosing RBD at an earlier rate, which increases proper diagnosing, and we lose the risk of underdiagnosing these patients. So, what do I want to do with this research in the future? I want to continue working on increasing the size and diversity of the data set. As I mentioned several times before, we only had a small data set to work with, so increasing the types of RBD that are being used and the variety of patients that were being tested in this data set could prevent overfitting and overall create a more reliable and accurate system. To add to this, I really want to use more advanced deep learning models, such as convolutional neural networks and in general deep learning models, for raw EEG pattern recognition and for more advanced diagnosing capabilities. My ultimate goal, however, is to transfer these diagnosing powers to medical wearable devices, such as EEG headbands and smart glasses, to open more doors for early intervention in neurodegenerative diseases and give patients a fighting chance before they become symptomatic years later. So thank you guys so much for listening to my presentation. I hope you learned something more about RBD and its capabilities with machine learning, and I'll be open for any questions. Thank you so much.
Excellent presentation. Thank you so much. That's a really good start with machine learning for today. Any questions?
Yeah.
Please go ahead. Go ahead.
So the model, were you able to, was the model able to tell you any specific by human observable in the EEG like indicators of RBD, or was it specifically like, oh, the model says, or the model is just able to tell you that person has RBD?
So yeah, I think it's more of the fact that the models will be able to tell you if it's RBD or not. So it kind of does that process for you. But as I said before, if we could complement it with more maybe human-based approaches, such as the polysomnography, we'll be able to complement those two. So we have two different viewpoints, not just relying on one over the other.
We have another question. Please go ahead. Do you, no. Any questions?
Yeah.
Is there any particular reason as to why you decided to do your project on RBD?
Yeah, so I've always really been interested in neuroscience, especially just how the brain worked. I did like a couple of classes on neuroscience myself, and I just wanted to understand what else in neuroscience besides kind of like the basic things that we all study. So I went on a little deep dive and I figured out, oh wow, RBD, I've never really heard of that before. This is really interesting. And then when I saw that connection to other neurodegenerative diseases like Parkinson's, I was like, this could be really interesting to study. So I think that's kind of what piqued my interest.
I'll go with one question if there is nothing else. I am a machine learning person. I'll try to keep it short and leave the other conversation out. So the first one is, you said there is like 16 unhealthy persons in your future extraction. Do you think the futures of the 16 are clearly distinct from the other 96 in terms of the power spectrum or the frequency? Is it like visibly significant difference?
I would say so, yeah. I think what I was saying before with like the theta and alpha, I think those two are definitely very, very significant in differentiating between patients with RBD and then healthy patients.
Let's say about 10-20% of the data difference. I saw the graph and it was like minimal in the graph.
Right.
Is it like significant data, significantly different? How would you say, like 10% of difference?
I think probably. I think with maybe more comprehensive signals, we'll be able to differentiate more because of the limited data set. But I think overall, like, I think I would just have to try and maybe use more like advanced capabilities in order to differentiate more. But for like this simple study for that, I think it was sort of significant for the purposes of my study.
This is really a very good study because I can see like a graduate study, graduate level full course of things happening from data sourcing to comparing of machine learning models. Just the final thought question would be, there are like 96 healthy and 16 unhealthy. So if we, without doing any machine learning, if we randomly pick one, the probability of it being healthy is like 80 to 90%.
Right.
So after machine learning, it comes out to be, if we say we are 90% accurate, that seems a little less because of the data set being just 96 and 16. So we need a little bit more features and probably a bigger data set.
Right.
Probably a very good project lies ahead of you. And I'm very happy how it ends. You mentioned about the hardware integration as well.
Right.
You put in glass while sleeping and collect data, it seems.
Mm-hmm.
Okay. Really good one. Thanks for sharing.
Yeah.
Any final questions? No. If not, thank you so much again.
Thank you so much.